So here's the first trick that everybody learns: integration by substitution. Integration by substitution. And what you want to remember is that, well, a lot of the tricks that are used in integration are basically applications of rules of differentiation. They're sort of counterparts. Counterparts of rules of differentiation, and this is the counterpart to the chain rule. So let's recall the chain rule. If you're taking the derivative, of some composed function, right? Then what do you get? What's the derivative of a composition? F composed with G. Yep. F prime G of x times G prime of x, right? The derivative of composition is this sort of thing. Right? That's to say that, in other words, F composed with G is an antiderivative of F prime G of x, G prime x. We've just written the same thing twice, right? That the derivative of this is that. In other words, this is an antiderivative of that. And I'll just write it again. An antiderivative of F prime G of x, G prime x dx is F of G of x plus C. Okay. Okay. Right, so is everyone all right? We've just written the same thing 3 times. Okay. May look different, but it's the same thing. Okay. So so now here's the example. Suppose somebody says find the antiderivative, evaluate sine cube x cosine x dx. Okay, so find the antiderivative of sine cubed x cosine x dx. Does anyone see, looking at this last phrasing of what we've said 3 times, does anyone see how to do that? Does anyone see the connection between this last thing down here and the problem? So think about it for 1 minute and see if you can recognize that that is an instance of this. Like what would your G be? What would your F be? Think about it for another 30 seconds, and then I'll ask you to talk to somebody next to you. Okay, talk to somebody next to you, please. Or behind you if there's somebody next to you. Okay. So we want to recognize this thing as f prime of g of x, g prime x dx, because if we do, then we can just say, oh, this is going to be f of g of x plus c, right? So what are we going to take as our g? What are we going to take as our g, Mohammed?
Sine of x.
G will be sine of x. G will be sine of x. Okay. And then g prime will be cosine x. Right? And what's f? What's f? Well, f prime then is going to be what? F prime. Go ahead, Mohammed.
X cubed.
X cubed, right? F prime is going to be the cubing function, right? Because you're taking the cube of sine of x, right? The cube of sine of x, right? So that's good, right? We've got the cube of sine of x times the cube of g of x times g prime of x dx, right? Right. So what's the answer? The answer is going to be f. Well, what's our f? F then is going to be x to the 4, right? And so you end up with sine of x to the 4 over 4 plus c. Okay. So this is using the chain rule in reverse. You'd see this thing and you'd say, oh look, this is actually f prime of g of x, g prime x dx, right? So after you do these things for a while, then it will be easy to recognize them. Okay, but there's actually a sort of a notational shorthand that people use that makes it a bit clearer. Okay, so that's called U substitution. So I'm gonna erase this. Is that all right? Okay, I'm gonna erase this. Okay. So there's sort of a change of notation. One introduces a convenient change of notation. Sort of like a abbreviation. So notational abbreviation. And it's called U substitution. It doesn't have to be U. You could use anything for the U. Okay. So you say, okay, I'm going to rewrite this. Right? Let U be sine of x. Let U be sine of x. Then I can rewrite this as du dx is cosine of x. So you rewrite the above as so sine cubed x cosine x dx. You rewrite as u cubed du. You rewrite this as u prime, I'm sorry, u cubed, the integral of u cubed du, maybe thinking of du as cosine x dx. Like the cosine x dx is sort of your du. Okay. There's actually a problem with doing that. Okay, but just do it anyway. Okay, so yeah, so there's a warning. One doesn't exactly. It's not exactly true that du dx equals cosine x allows you to say that du is cosine x dx. Okay, it's not exactly true. And later on in your calculus life, which seems to be a convenient term today, in your calculus life, you will later see things like this, that if you take the derivative of f with respect to t, you get partial of f with respect to u, du dt, plus partial of f with respect to v, du dt. When you start doing multivariable stuff, you'll see things like this. And that will maybe bother you because you think, oh, what happens, I thought I could cancel out these things, I could multiply these things. It looks like I'm getting df dt is 2f dt or 2 df dt or something like that. Okay, so it's not exactly legal. It makes sense in the one variable, it will work in the one variable case, but it's sort of theoretically unsound to think of this as some sort of multiplication. Okay. In any case, unsound or not, it works now, and we're going to think like that. Okay. Okay. I mean, really, what this is of course that all you're doing is writing this as u of x cubed u prime x dx. Right. So it's the same thing that we were doing before. Okay, so, but one uses this abbreviation to make it simpler. So, your u is the g that we had before. Okay. In any case, one does this thing. Okay, and you say, okay, now I'm looking for the antiderivative of u, right? Of u cubed. So that's going to be u to the fourth over 4. Let's see. And then I go backwards and I say, well, my u, I want it in terms of x, so I'm going to write this as sine to the fourth x over 4 plus c. So it's sort of a handy notational trick. If you don't want to think in terms of f and g, you can you can replace everything. Find a convenient u, and then integrate. Find the antiderivative with respect to u, and then switch back to x at the end. So, but really what's going on, of course, is this. Really what's going on is that we're using the chain rule in reverse. So, yeah, so let's try some. So here's one. So do this by u substitution, find a convenient u. And you notice that what you're going to want is you're going to want a u whose du is there. Right? So you want to find a u for which a du is convenient, is there. So choose your u wisely. Maybe I should decide. Let me start off with the simpler ones. X squared plus 1 equals 7, 2x. So I didn't notice. Okay, so try this. Take half a minute and see if you can get it. Okay. Turn to somebody next to you and say what you're getting.
Yeah. Right.
Okay. That's a 7. Sorry. It's a 7. Okay, so what is it? What is it? What do you take as your u? I'm going to take what? X squared plus 1, right? Then the u dx is going to be 2x. And so you write this thing as u to the 7th, the u, you integrate, u to the 8 over 8 plus c. That's going to be x squared plus 1 over 8 plus c. Right?
Doesn't your x squared plus 1
To the 8, sorry. Okay. Another example. If I had, okay, so this is not really an example. So if I didn't have the 2 there, right? If I didn't have the 2 there, what can you do? Here's what I'm going to do. I'm just going to put the 2 in. Okay, right? But I can't just do that whenever I feel like it. Right? So let me also put a 1/2 here. So I'm multiplying by 1. Right? I multiply by a clever choice of 1, and then at the end, right, I'm going to get 1/2, right, so u to the 8th over 16 plus c, right, and I end up with x squared plus 1 to the 8th over 16 plus c.
So we should put the 1.
Hmm?
So we should put the 1.
Yeah, I mean, you can't just, if this is the problem, you can't just throw in a 2, right?
Yeah.
You have to, but it's certainly legal to multiply by 1, right? You can always multiply by 1. So I'm going to multiply by 1. Right. Using the fact that, the antiderivative of a multiple is a multiple of that of the antiderivative. Okay, so everyone all right with that? Any questions? Hey, do you have a question?
I don't see why you started out with this one thing.
Yes.
And then you changed it to 1/2.
Well,
Why did you do that?
Sorry, this is the second problem.
Oh,
Okay,
is
here's the second problem.
Okay.
Here it is. Suppose I ask you to integrate this, and there's no 2 there.
Right.
So you say, oh, okay, I want my I'm going to take as my u x squared plus 1, my du dx that is 2x. I don't have a 2x here.
Right, so you can multiply
Right.
by
So I'm going to multiply this by 2, but I can't do that just by whim. I have to I have to balance it out by multiplying by half also.
Okay.
So you start off with this, and then you throw in the 2 to make it work. Okay. Okay, now let's do the one that I had on at the beginning. Okay. Again, take half a minute. Okay, turn to somebody and say what you're taking as your u. Okay, so what is u? What are you taking as your u? Ellen, that's great. Right, and why do you do that? Well, why do you do that? Because you see that du dx is in there. So you end up with u du c squared over 2 plus c. That's to say natural log squared over 2. Okay. Next one. It's the same sort of thing. The square root of the natural log over x. Right? Somebody tell me what to do. What am I going to take as my u? Go ahead. I think you said it first, Charlie. Ln(x), right? So let's take let u be ln(x), du dx is again over x, and this is u to the 1/2 du. So you get u to the 3/2, 2/3 u to the 3/2. See, in other words, 2/3 natural log x to 3/2 x. Okay, everyone all right? Pretty straightforward. Last example. Last one. Take a minute and see if you can evaluate the whole thing. Find the antiderivative. Okay, turn to somebody next to you and say what you're doing. See if you're doing the same sort of thing.
And then you yeah. So that it would be, I think, supposed to use the negative because you would be adding 1 power and dividing it. And then you have the constant at times 2 upon 3. No, I'm showing just parallel.
So we're getting negative 4?
No, because it's negative for the and then you divide it, and then you divide that. You treat it like so.
substituting one.
Oh, yeah.
Yes.
Oh, right. I forgot to give it back to you. Wait.
Okay, who would like to say what we need to do? What do we need to do? What are you going to take as your U? Leanna?
My U was 2 plus x to the 3 halves.
Okay.
And then for the dx is 3 over 2 times x to the 1 half.
Okay, great. Right, so then you say, okay, well, I'd like to have, so right now I have a u cubed on the bottom, right? I have a u cubed on the bottom here, but I've only got the x to the 1 half. I'd like to have 3 halves x to the 1 half, so I make it 3 halves x to the 1 half, and throw in the 2/3 to make sure that's okay. So then I've got, then that gives me the du. Yes, Shannon. Where did the 1 come from? I've got, this is u cubed on the bottom,
Yes.
right? So it's 1 over u cubed.
Oh, okay.
Okay. Okay. Don't worry, I've done worse than that.
Oh, I remember what you did the 2/3, 3 half thing. Sorry.
Okay. Let me, again, it's probably my bad board work. So let me not be lazy and just work this out. I have 1 over 2 plus x to 3 halves cubed. I have square root of x dx. Right? I'm going to put the 3 halves in here and 2/3 over here, so that it's more clearly so that it's more clearly the integral of 1 over u cubed d. Right, so u of -2. So you get u of -2 over -2, right, over -2 times 2/3. Right? In other words, negative 1/3 u squared plus c. In other words, negative 1 over 3 u squared, u was this thing, 2 plus x to the 3 halves squared. Plus c. Okay. Okay. Any questions? Have I made mistakes? It's quite possible. Any questions about that? The other day I was tired and reading a book, Thomas the Train, to my son, and I said something, Thomas, it's okay because he's differentiable. And my son said, what? And then he kept on repeating this, Thomas, it's okay, he's differentiable. Yeah. Any questions about this?
Did you just move the u to the -2 on top so that way it was easier to work with?
Just for that of it, yeah. I see. For me, whenever I see this u 1 over u cubed, I think of it as u to the -3, right? Because then you take u to the n plus 1 over n plus 1. You don't need to move it. You don't need to move it. Okay. So that is that's the antiderivative part of substitution. Okay. So use substitution to get antiderivatives is what we just did. Now there's the second part to that, which is use substitution and definite integrals. Okay. So substitution and definite integrals. substitution and antiderivatives, or substitution and indefinite integrals, and now we're doing substitution and definite integrals. Okay. So the same sort of idea. Like somebody gives you this integral f prime g of x d prime x dx between a and b. Right? Between a and b. Well, we know that the antiderivative of this is f composed with g. Right? We know that the antiderivative, by the chain rule, the antiderivative of this is f composed with g. So, by the fundamental theorem of calculus, this is going to be f composed with g at b minus f composed with g at a. Right? By the fundamental theorem of calculus. You take the antiderivative and take the difference at the endpoints. Right? In other words, f of g of b minus f of g of a. Okay? Everyone okay with that? Okay. Okay, so now if I took a u substitution, say we let u be g of x. Okay. Then this is going to be f prime of u du. Right? The antiderivative of f prime is just f. So this is going to be f between f of u, right, between, let's call it, I don't know, alpha and beta. No, let's not use alpha and beta. Big X and big Y. So what should my big X and big Y be for this to be right? In order to get the same answer, what should my big X and big Y be? Should they be b and a? I'm going to get f of b minus b of a, f of a. Is that right? We get the same answer if I take those as those as the bounds of my new integral? It'll be g of b and g of a. Yeah. So if I take g of b and g of a, right, then I get g of b and g of a, it's f of g of b minus f of g of a. Okay. So in other words, if you do your u substitution, you can use the u. You can evaluate the definite integral entirely in u, but you have to change the bounds of integration. Okay, this is u when x is b. This is u when x is a. The point is that one can evaluate the definite integral in u, but you must adjust the bounds of integration. Okay, you can't integrate. This one is going from x, as x goes from a to b, right? This one you don't want u to go from a to b, but you want it to go from whatever u is at x equals a to whatever u is at x equals b. So let me do me do a concrete example of this. So, so somebody gives me an integral, the integral from 1 to 2 of t squared minus t to the fifth 2t minus 1 dt. Okay. So let's do our u substitution. Let u be t squared minus t, right? Then du dt is of course 2t minus 1. We can rewrite this as the integral from u to the fifth du, right? But we have to change the bounds of integration now, right? So when t is 1, what's u? Well, u is 0. Right. When t is 2, u is 2 squared minus 2. In other words, 2. Okay, right, that's u when t is 2. I've got u when t is 1, u when 2 is 2. Right? Or better, is to think that this u is secretly a function of t, right? This u is secretly a function of t, and so really what this is u of 1, and this is u of 2. Okay, so you adjust the integral, right? And you say, okay, so this is going to be u to the 6 over 6 between 0 and 2. Right? U to the 6th is 64, right? 2 to the 6th is 64, right? So you have 32 thirds. No, we don't. We don't. As long as you could. Okay, so you can, let me get to that in a second. Okay, so there's another way of doing it. But let's just stick with this one first. Okay. So here it is, right? You do your u substitution, right? You change your integral to 1 in u. And you say, okay, I'm going to evaluate this integral between u of 1 and u of 2 because t was going from 1 to 2. I'm going to evaluate u between u of 1, evaluate this guy between u of 1 and u of 2. Okay, and then you get the value. Okay, there's another way of doing it using just the anti-differentiation before. So there's another way. Okay, you could say, well, I'm going to go like this. Use only the antiderivative part. So you say, well, this thing, I'm only going to think about the antiderivative. I'm not going to think about the definite integral. I'm only going to think about the antiderivative. Okay? And I'm going to use substitution to obtain only the antiderivative. So you say, okay, I'm not going to go for the definite integral. I'm only going to go for the antiderivative. I do the same substitution. I get u to the fifth. This is u to the 6 over 6 plus c. Okay, which is going back to the t's. That's going to be t squared minus t over to the 6th over 6 plus c. Okay, and then you say, then you go back, so return to the to the definite integral. Say, well, then that definite integral that I was interested in is going to be the difference of the antiderivative at the endpoints, 1 and 2. Right? So you switch back entirely to t. You switch back entirely to t. You say, okay, well that's going to be 2 squared minus 2 to the 6 over 6 minus 1 squared minus 1 to the 6 over 6. That is to say, 2 to the 6 over 6 minus 0 again. Okay. So the U substitution gives you two ways of approaching definite integrals. You can either say, okay, let me use U substitution. You can either say, well, I'm going to use U substitution to get the antiderivative, right? So you say, let's figure out what the antiderivative, and then evaluate that between evaluate the difference between the endpoints here, right? Or shorter is you say, I'm going to switch my integral over to the U world, into the U variable. I'm going to change variables. This is usually called change of variables. I'm going to change variables. And I'm going to change my integral to 1, to 1 in U, but I have to adjust the bounds of integration in order to get the right answer. So I do my thing entirely in U. I don't switch back. Okay, I don't switch back. You could at this point say, I'm going to switch back to p squared minus p to the 6 over 6 between 1 and 2. But why?